Okay, in the previous lecture that we started, we will study that 4 different case studies, right. So, first one is that in the previous lecture we might have discussed for 2 minutes only, right. So, about this first case study, that first thing is that unit 2 and unit 4, right, unit 2 and unit 4 are under load following control contract only, right. So, they will not be part of AGC, that generation will actually change the contracted demand, right, and unit 1 and unit 3 are speed regulation purpose only. That means that there will be no supplementary controller, that means Ki1 and Ki2 will be 0 and it will be only speed regulation purpose, that is your delta F by R feedback that is coming no for the governor. So, further no centralized supplementary control is available, that is Ki1 Ki2 is 0. So, that is why I told you that Ki1 Ki2 is 0. Now, all the distribution companies, in short we call DISCOs, have a total load demand of 0.005 per unit megawatt. Here we have taken very small load disturbance 0.005, I mean load demand, because we have considered the generation rate constant of 10% per minute for the thermal unit, right. Actually generation rate constant actually deteriorates the dynamic responses. So, if we take because if you take instead of 0.005, if you take 0.001 or something, the settling time also will increase, right, a lot of oscillations will be there. So, even with 0.005 per unit megawatt, right, for your what you call total that all the load demanded by DISCOs, that is DISCO 1, DISCO 2, DISCO 3 and DISCO 4, right. So, is contracted to the various generating unit as per the DPM. So, this distribution this DISCO participation matrix is considered like this. So, you know that I am making in short, distribution company means that this is D1, this is D2, this is D3 and this is D per. Generation company means G1 instead of GENCOs, G2, G3 and this is G4, right. So, unit that is your unit 1 in area 1, it is not taking part in load following. That is why this all these elements actually it is actually your what you call that G1 is not generating unit 1 is not that is your in this case GENCO, no, it is unit 1. Let me just delete this one. This is D1, this is D2, this is D3, actually this is load following. It is unit 1, unit 1, unit 2, unit 3, unit 4, right. So, this is in area 1, say A1 and these 2 units are in area 2. So, in area 1 that generating unit 1, right, it is not taking part in load following, right. So, in that is why this all these elements, that is CPF 11, CPF 12, CPF 13 and CPF 14 are 0. Similarly, that unit 3 in area 2 also not taking part in load following, right. So, that is why CPF 31, CPF 32, CPF 34 and 33 and CPF 34, these all these things are 0, right. And then that unit 2, that is unit 2, this one, right, that is your unit 2 taking part in load following and unit 4 in area 2 also taking part in load following, and this is their CPF values, but all the time this column summation it should be always your 1, right, that I explain why it is. So, this is equation 16. So, this is that DPM has been considered for this case, right. It may be noted that since unit 1 and unit 3 are not in load following, the corresponding rows in the DPM have all zeros entries and also K1, K3 is 0, because it is not taking part in load following, and that load following controller gain for unit 1 was K1 and for unit 3 was K3, that was shown in the block diagram. So, K1 is equal to K3 is equal to 0, right. Also we are assuming that there is no uncontracted power demand in the both the areas. So, no uncontracted power demand. So, that is delta PL1 UC, that is uncontracted, the abbreviation delta PL2 UC is equal to 0, right. As mentioned before, that each DISCO has a total load demand of 0.005 per unit megawatt, that is delta PL1 is equal to delta PL2 is equal to delta PL3 is equal to delta PL4 is equal to 0.005 per unit megawatt, right. and delta PL1 local same as before, that is delta PL1 plus delta PL2. So, 0.005 plus 0.005 per unit megawatt, that is actually 0.01 per unit megawatt, that is delta PL1 local. Similarly, this load disturbance we have taken this discos are same, you can take different also, you will get the desired result. So, delta PL2 local is equal to delta PL3 plus delta PL4. So, this is 0.005 plus 0.005 per unit megawatt, that is delta PL2 local will be 0.01 per unit megawatt, right. Now, at steady state, the power generation of each generating unit is equal to the contracted power of the respective generating unit as given by equation 3 that we have seen before, right. So, thus delta PGISS will be the steady state generating power will generated power by unit I will be delta PGCI, the contracted power, that is your contract power of GENCO unit I, right. So, this way we can make it delta PGC1, delta PGC2, delta PGC3, delta PGC4 is equal to this DPM, that is into delta PL1, delta PL2, delta PL3, delta PL4, right. So, if you calculate all, so delta PGC1 will be PGC1 will be 0, delta PGC3 will be 0. So, delta PGC2 and delta PGC4, these two are contracted demand. So, delta PGC2 just you multiply this one with this delta PL1, delta PL2, PL3 and delta PL4. So, you will get delta PGC2 will become actually 0.0085 per unit megawatt, right, and delta PG1 and PGC3 is 0. Similarly, delta PGC4 you calculate, you will get 0.0115 per unit megawatt, right. So, this is actually your what you call that is steady state, that is contracted power demand, and your at steady state that your this is delta PGC2, that is that discos have all the discos, that total contracted power demand that has to be generated by this unit 2. So, that is actually this is actually is equal to that delta PG steady state, it because generation will follow the load. So, at steady state this value will come. Similarly, for unit 4 at steady state this value must reach, right. So, therefore, delta PGC1 was 0. So, at steady state delta PG1 SS will be 0 and delta PG2 SS is 0.0085 megawatt, because that is equal to delta PGC2. So, delta PG3 steady state is equal to delta PGC3 is equal to 0 and delta PG4 SS is equal to delta PGC4 is equal to 0.0115 megawatt, right. So, this is contracted power, tie line power. Now, scheduled tie line power flow, that is equation 4, that we know this, that delta P tie 1 to schedule, this formula we know, that I is equal to 1 to 2, J is equal to 3 to 4, CPF Ij delta PLJ, this is valid for only that our system, minus I general one I did not make it, right, but your just for 2 or 3 areas your there is no need actually, right, and I is equal to 3 to 4 and sigma and j is equal to 1 to 2 CPF Ij delta PLJ. But I request you that when you will go through this write down in terms of GENCO and DISCO, you will easily can write it, right. So, now delta P tie 1 to schedule, right, that is equal to this much, that all this term CPF 13 delta PL3 plus CPF 14 delta PL4 plus CPF 23 delta PL3 plus CPF 24 delta PL4 minus CPF 31 delta PL1 all in bracket minus in bracket CPF 31 delta PL1 plus CPF 32 delta PL2 plus CPF 41 delta PL1 plus CPF 42 delta PL2. So, bracket close. So, CPF 13 is equal to CPF 14 is equal to 0, CPF 23 is equal to 0.75 and CPF 24 0.6, right. CPF 31 and CPF 32 both are zeros, that is from the DPM whatever DPM we have taken from that only, and CPF 41 is 0.75 and CPF 42 is 0.9. Now, that regarding this tie power actually that just I have made it that actually that your for you can if it is for 2 area system that you have unit 1, unit 2, unit 3, unit 4, this is your unit 1, unit 2, unit 3, unit 4, right, and this is my distribution company 1, 2, 3 and 4, right. So, that tie line power flow equation actually if you look into that, this block actually disco 1, disco 2 only have contact with this units with this own area. So, this term will not appear in the tie line power flow equation. Similarly, if you look into that disco 3, disco 4, it has that unit 3, unit 4, right. This is unit 3, this is unit 4. This has only in that area 2, this contact disco 3, disco 4 in area 2, and it has it may have contact with only unit 3 and unit 4 in its own area, if any, right. So, this kind of thing there will be no schedule power flow. For example, in the first case, I mean previously we have taken 3 cases for that your what you call that for deregulated system. At that time we took from 0.5, 0.5, 0.5 and 0.5. So, there was no schedule power, it was 0, but only thing is that when area 1 and area 2 we are taking the direction from 1 to 2. So, disco 3 and disco 4 are in area 2. So, disco 3 and disco 4 actually has contact with GENCO 1 and GENCO 2 in area 1. So, in the direction of 1 to 2, that is why this term is written first, minus that disco 1 and disco 2 actually it is trying to draw power from the GENCO 3 and GENCO unit 3 and unit 4 of area 2, that is why it is this one minus that one. So, when you will make it, right. So, if you make this if you isolate this all this your discos and unit 1 in that own area, then only this matrix will be there and this matrix will be there. So, from that you can write as it is direction in the direction that is from 1 to 2, right. So, that is why CPF 13 delta PL3 plus CPF 14 delta PL4 plus CPF 23 delta PL4 plus CPF 24 CPF 23 delta PL3 plus CPF 24 delta PL4 minus, if you look into this, that CPF your 31 delta PL1 plus CPF 32 delta PL2 plus CPF 41 your delta PL1 plus CPF 42 delta PL2. So, this all these thing you add up, multiplication this minus bracket all these things you add up, and that is actually tie line power flow from in the direction of 1 to 2. So, earlier I have not told, but here whatever way I mean if you cannot recall those formulas, simply you construct and make it like this, and easily you can get the power flow, say either in the direction of 1 2 or in the direction of 2 1. If you want in the direction of 2 1, then this one should come first minus this one should come first, right. So, this is that your what you call this is your I mean ideas. So, basically when you take CPF 13, CPF 14, only 2 units are there, right. So, in that case you can I mean what you call you can easily make it, right. So, next is that delta PL1, delta PL2, all these things are given. So, 0.005 per unit megawatt. So, all these CPF values you substitute here, you just put all the CPF value and all delta PLs are same, you just put it, then you will get that it is 0.75 plus 0.6 minus in bracket 0.75 plus 0.9 into 0.005. So, it should come minus 0.0015 per unit megawatt. So, schedule power flow it is showing minus, that means actual direction of the power actually from area 2 to area 1, because delta P1 is minus, right. So, in this case the generation rate constant is taken as 10% per minute, right. Actually 10% per minute means it is your 0.1, right, per unit megawatt, right, per minute, right, that is a 10%. So, that means if you want to make it in second, that is 0.1 divided by 60 per unit megawatt per second, right. So, that means generation rate constant values are actually we have taken 0.1 divided by 60 per unit megawatt per second, right. So, that is why this generation 10% per minute is considered. Only thing I would like to tell you, this all these things simulation thing result whatever I am saying for purpose of our understanding, actually the code was written, it was not directly not through the Simulink, only code was written, data were generated, then it was plotted in the MATLAB environment, right. So, now dynamic responses are shown in figure 3 and 4 respectively. So, if you see the dynamic responses, right, we will go one by one. So, if you see that frequency deviation actually it is steady state, it is 0, actually settling here only, but although 150 seconds plot was shown, but less than 50 second it will be somewhere around that. So, around 25-26 second it is more or less settled, right. Similarly, for frequency area 2, this is also settling. Long we have given 150, but mark before that actually it is settling, right. After, but only thing is that if you do not consider GRC, right, if you do not consider GRC, then peak deviation also will be less. Here it is minus 0.08 hertz approximately, that frequency 1. Similarly, for area 2 also minus 0.08 hertz the peak deviation, but if you do not consider GRC, it will be very less, maybe minus 0.023 or 0.24 hertz or even less, right. So, without GRC. So, frequency, this is frequency deviation, and steady state as desired, that it is your what you call that deviation is 0. So, next is this is your the tie line power and actual and error, right. So, actual will be that your this was your what you call that your actual power, that is your minus 0.0015, that is it is actually 10 to the power minus 3, right. So, whatever is given scale into 10 to the power minus 3, and it is coming minus 0.0015 per unit megawatt, and a steady state that your delta p tie 1 to error will be 0, because actual will match to the schedule value. So, that is why this dash line is error, dash line is the your delta p tie 1 to error, right, and that is actually a steady state, it is becoming 0, but oscillations are there. This is due to your what you call due to your that your generation rate constant, and if you look into these two curve, both actually it is both are your what you call in the same shape, only their scale has shifted because of this thing, because it is delta p tie error is equal to actual minus schedule, right. So, just scale has shifted, otherwise their nature is totally identical, right. So, this is my your what you call that your frequency and tie power. Next we will see the generation. Now, if we come to the generation, one interesting point is that I will come to that. First see delta Pg1 steady state, right. So, the dashed one delta Pg1 is your dashed one. So, it has come to 0, because unit 1 was not in load following, and also we did not put any load frequency controller, and delta Pg2, right. So, it was in the load following, and it is reaching to this value, I mean steady state value, right. I exact your values are there on top, just let me see it, right. I cannot recall these things, I think it is 0.0085, right. Just let me see that your what was that value, this delta Pg2 have 0.0085 and delta Pg4 0.0115. So, here it is actually going to the steady state, right. So, at steady state this is actually going to that by your 0.0085, that is delta Pg2, because it was in the load following, because contacted load demand was 0.0085. So, generation is chase the load and this is also your more or less settling at this time, right. It is less than 100. So, actually all are supposed to actually, because of this plotting and that units, right. That is why perhaps it appears that here it has settled in 27, 28 or 30 second frequency and tie power, right, but still not exactly it is what you call that exactly 0, right. So, some difference is there, that is why it is depending on the scale, right. So, that is why it appears that it is still going, but their value is very negligible, whatever scale you show into it is minus 3, right. So, delta Pg1 unit 1 it is going to 0, and delta Pg2 it is going to this value, right. So, similarly, for delta Pg3 and Pg4 plotted as well. So, delta Pg3 here also it is going to 0, because steady state it was 0, and delta Pg4 it is going to steady state I think minus 0.00115, right. So, that is actually generated by the unit 4, right. So, steady state value it is matching. Now, interesting point is that if you look into the responses, that generation responses initially, right, actually it is a ramp increase or ramp decrease, right. That I told that when we are discussing about generation rate constant, that is your delta Pg say for ith unit k is equal to delta Pg for ith unit k minus 1 that we have discussed plus minus r into delta t. So, in the simulation that r I told you that we have taken the 10% per minute. So, that is 0.1 divided by 60 per unit megawatt per second, right. So, every time that generation rate were checked, right. So, and whenever you see the ramp type of responses, right, at that time you will find the generation your what you call limit was violated. So, when its ramp increase means at that time that your delta in general I am just putting delta Pg for ith unit that dot, right, at that time it was greater than 0. So, that is why the plus sign delta Pgi k is equal to delta Pgi k minus 1 plus r delta t, right. When delta Pgi was your first thing is it was greater than 0 and second thing is that absolute before that absolute value of this one was greater than r, right. So, when first you have to check that is greater than r or not, and then you have to check if greater than r absolute greater than r, first you check that delta Pgi greater than 0 or not, dot greater than 0. If it is so, then it has to be constant by delta Pgi k is equal to delta Pgi k minus 1 plus r into delta t. So, as long as this graph is going like this going like this, right. So, that means it is ramp increase because generation rate is violated. Again for it is absolute first you are checking. Now, again when it is your delta Pgi dot, right. Now, you have to if it is less, first it is checked violated or not. If it is less than 0, delta Pgi dot less than 0, that is negative, but it is then this delta Pgi k will be delta Pgi k minus 1 minus r into your delta t. That is why it is ramp increase, ramp decrease, as long as this constant will be violated. But when constant will not be violated, say this region, in this region or in this region, at that time within this band you will find that small oscillations are there. Otherwise, this generation responses whatever you will see like a straight line, it will go up, go down, go, because that constant is violated, right. Those constant is violated, generation rate is violated. That is why the because of generation rate violated, that is why your response of frequency or time power deviation all getting deteriorated, including the generation responses. So, that is the reason that your GRC effect, right. So, this is also that this increase or decrease just because, and only when some oscillations is there, at that point you will find GRC is not violated, right. So, this is actually your what you call that why it is looks like ramp increase or ramp decrease of the generation. So, this is your for the case 1. Now, first case. Now, case 2 actually now first one I have by this thing I have written case A, make it case 1. So, this is case 2. In this case what we are doing is that unit 1 and unit 2 are under AGC only, while unit 2 and unit 4 are under load following only. So, unit 1 and unit 2 are under your are under AGC. So, the DPM remaining the same as given by equation 16 case 1, first one I have written actually it is case A, right. So, better you make it case 1, right. Since in each area that means I will go to that your block diagram once again, that your in this case that your unit 1 and unit 3 are under AGC only, while unit 2 and unit 4 are under load following only, right. So, if unit 2 and unit 1 are under AGC, right. So, I will go to that block diagram once again such that it will be easy for you to realize this. So, just hold on, let me reduce the size, right. So, as unit 1 and unit 3, right, it was now unit 1, if unit 1 and unit 3 if they are in your what you call in AGC, right. So, this is my unit 1 and this is my unit 3, right. So, if these two are in AGC and unit 2, this is unit 2, this is under load following, this is under load following, and unit 4 under load following. So, unit 1 and AGC means that, and this is only load following means that APF 1 is 1, right. APF 1 is is equal to 1.0 and APF2 actually it will be 0.0, right. So, that means this term should not be there. So, unit 1 only is under, and here your K1 has to be 0, because unit 1 is not under load following. So, this thing also should not be there, only simple unit, right, simple the way we have done it before. And in the case of your unit 2 is under load following, so this K2 will be there, right, but APF2 is 0. So, this thing should not be there. Similarly, here also that unit 3 is under AGC, that means my APF this is APF3, this value should be 1.0 and this is should not be there, this value should be 0, right, and here it is K3 as it is under AGC, right. So, K3 should be 0, that means this block should not be, this load following controller should not be there, but and in this case it will be there, it is under load following. So, that way your so many cases you can generate, right. Therefore, let me go to that go back to that case 2, this one. So, in this case you are under AGC I told you, and unit 2 unit 4 are under load following only. So, DPM, that disco participation matrix, it remains same as by equation 16. So, same disco DPM has been considered identical, right. See, in each area only one generating unit is under AGC, its AC participation factor is unity. I told you APF1 will be 1.0 and APF3 will be 1.0, APF2 will be 0 and APF4 will be 0. So, the AC participation factors of the units under load following only are 0. So, APF2 is 0 and APF4 is equal to 0, right. So, as in case 1, same data taken, delta PL1 is equal to delta PL2 is equal to delta PL3 is equal to delta PL4, that is 0.005 per unit megawatt, right, and no uncontracted demand was there. So, delta PL1 UC is equal to delta PL2 UC is equal to 0.0. Therefore, as steady state we have seen earlier, delta PG1 SS same as before, it will be 0.0, delta PG2 SS same as before 0.0085 per unit megawatt, because DPM remains same. So, these things will be same and uncontracted power demand is not there, that means 0. Therefore, delta PG3 SS will be 0.0 and delta PG4 steady state will be 0.0115 per unit megawatt, same as before. So, and delta P tie 1 to schedule also is equal to minus 0.0015 per unit megawatt, right. So, thank you very much, we will back again.